Tau is 2 again. When you fix tau and then as you move from delta 1 to delta 2, you get this curve, which is this one. Little bit more wet than the bold one. And then when you fix tau to 1, then you could get these two curves, this one and this one. So basically what it means is that as the correlation, as the association increases, subjects with the little spatial association would have, and smaller variances would have the most influence on the tau's posterior, on beta's posterior. This you'll also see that when I derive the posterior estimates of beta. Now when you concentrate on Zi, which is a linear combination of all responses for subject I, this is how Zi looks like. Look at this expression Bj by sigma ij square, which controls the relative weight of response type J. And this vector Ki is defined as this, which controls the relative weight of observation at location S. What it means here is that the observation in the gaps between the teeth, which have 3 neighbors, have the highest spatial weight Ks. So since they have more neighbors, they contribute to more spatial weight, where they contribute to a higher value of Zi. Whereas the observations in the back of the mouth, that means that are the tooth number 7s, the 2 sides on 7, they have 2 neighbors, and those are the molar regions. Back of the mouth and the sides of the teeth get lesser weight. So we found out that the weight also varies. And now this is considered based on my adjacency matrix. If this becomes more prominent if you have the adjacency structure little bit different than 2 and 3. I mean, you can come up with your most structure, and then it becomes more prominent. That the more the number of neighbors has, that has quite a bit of variation than the one that experiences a lesser number of neighbors. I'm trying to propose some simulation scheme to go with to elaborate the methodology. I'm choosing 100 data sets with 50 subjects, and I'm choosing half a jaw. So instead of 168 sites, I'm choosing 42 sites, because there will be 7 tooth in a half a jaw. 42 means like just half a jaw means just one quadrant, not even the full jaw, and a single continuous response. So in a half quadrant, you will have 7 teeth, and then each teeth will contribute 6 sides. So that's how 42 comes here. We choose 6 subject level covariates, each coming from normal 0, 1 with this regressors beta. And data for subject I is generated like this, like mu I coming from this normal distribution. Now the probability YIS when it is observed is generated from this distribution, and then YIS given YS observed follows normal mu IS and sigma I square. Now 2 cases we are considering. We are considering homoscedastic sigma I square equals to tau I. Sigma is the error variance, tau is the spatial variance, fixing it to be 1. And here it is varying with respect to whether I is odd or even. And we consider cases where B0 is 0 and 1. Remember, when B0 is 0, you are not modeling the informative absence or presence of component. And here you are modeling it. Here are our simulation scheme designs. We choose rho to be 0.9. So we keep rho to be high because, as I mentioned, that rho 0.8 and rho 0.9 denotes means some kind of spatial association is there. Rho 0.2 usually they don't mean anything. So this is how we generate my data. Rho is 0.9, B0 is 0, and then I keep sigma I square tau I square to be 1. So this is a spatially correlated and homoscedastic model, the first one. Then the second one, the design is 1 with this heteroscedastic assumption, sigma I square tau I square is this. The third one is 1 with informative presence, because I put B0 as 1. And the fourth one is 2 with the informative presence. That is heteroscedastic, spatial, plus you have the B0 equals to 1. And now I'm fitting 5 different models. First, I'm considering a linear regression. That is just yi bar over all the sides for subject I. Second one, the next model under consideration is the spatial model without any informative presence and subject-specific variances. That is, I'm considering B0 as 0. Then all the sigma I square is sigma, tau I is tau. Third model, spatial without informative presence, that is B0 is again 0, but I'm considering sigma I and tau I. So I'm going in hierarchy. Then the fourth one is spatial model with informative presence, that is I'm considering B0 not equal to 0, but without any subject specific variances, that is more like 2, but I have B0 not equal to 0. And 5 is the full spatial model, where I have the spatial association, I have B0 not equal to 0, and then I have sigma I square tau I square. Computing overall mean square error for all the parameters taken together, and then the relative bias. And I present proportion of 95% credible interval that excludes 0. So some kind of a Bayesian power to see how things look like. So this is the result from my design 1, which is spatially correlated and homoscedastic. As you can obviously see, this correlates to more like model 2 here, because this is our design 1, and then like the spatial and then homoscedastic, so it should correspond to 2 here. So you can see that linear regression works fine in this case. So you do not have to worry about so many things. I mean, even with a rho equals to 0.9, simple linear regression is pretty strong. It's working very well here. But there is a little bit of, model 2 is slightly better than that. Now, as you move to design 2, the spatially correlated and heteroscedastic is your design. You can see that model 1 and 2 do not perform well. So what I get here from this simulation, what I get here from these two slides is that the assumption of homoscedasticity and heteroscedasticity has a lot to do here for this type of data structure, if you believe that they are coming from that design. Models 1 and 2 do not perform well. You can see the mean square error. This is overall mean square for all the parameters. When you go to model 3 and 5 that has the subject specific variances, they provide quite a bit of improvement in mean square error, 0.18 and 0.17. Homoscedasticity assumption was in model 4, so you end up with this power, and then this is the mean square error. Now, if you properly account for the spatial correlation and then all the features together, then you improve your power for beta 6, because I'm presenting only for beta 6 by this much percent, like 188, because you jump from 0.51 to 0.96. This is based on 100 data sets. And the reviewers did not have any other issue with that. I mean, they did not ask for larger size. So I think it is okay for this point. I mean, we ran it for lot larger, like n equals to 1,000, and got similar kind of numbers. Now, when we move to design 3, which considers spatial correlation, homoscedastic, and informative presence, you can see that models 4 and 5 do model informative presence B naught as not equal to 0, so they are doing good. So they are consistently identifying B0 as non-zero. These have bias. We have some negative bias, and model 4 and 5 are very close. The most interesting slide is this one. When you generate your data from spatially correlated, heteroscedastic, informative presence, then you jump from 0.26 from a linear regression to 0.94 for this parameter. Look at the change in the mean square error, 0.193, and then these are the estimates of relative bias for beta 6. So based on this simulation study, what we feel is that if you think that the data set has all these characteristics, we have to model the data and then figure out what the parameter estimates are. This shows that if you properly exploit all the structures, if you believe that the data has those structures, then these are the gain that you might get by using all the things in a unified framework. Now I'm going to the applications. We have two situations here. Like we are playing with 4 models. So I'm dividing between subject specific variances, and I'm assuming rho I squared to be rho here. Now this did not change that much. To keep things simple, I'm assuming rho I as rho. That is a uniform rho for all the subjects, which is not varying with respect to subject. So I assume spatial association to be coming from uniform 0, 1 and independence. That is, there is no rho, no spatial association. And then I have informative presence, and then not modeling informative presence. In case 2, I have 4 models with the same variance for all subject. That is, you have sigma ij square as sigma j square. Of course, the variances are varying with respect to the type of the response, because j denotes the type, that is pocket depth or attachment loss or bleeding on probing. Tau I as tau, and again rho I as rho. I assume 4 different cases: facial association and nose association, informative presence, and not modeling informative presence. Pretty busy slide, but I'm going to explain you what it's doing. So here there are the 4 types of situation: spatial and informative missingness. This is the full model. So here I'm presenting the 95% credible intervals to show you how the coverages are. You can see that here age is believed to be very cumulative, and periodontal disease, all the responses, pocket depth, attachment loss should be, age should be highly predicting that. That's very common in this type of research. If you do not assume anything, then this is what you get, the credible intervals, whereas you end up in this 0.023, so you do not include 0. You can think to be age to be positively predicting. Now female, that is, I coded female as 1, male as 0. So here what you're saying is, in spite of the imbalance, as I mentioned earlier, 73% of them are females. What you get here is that males do have a worse type of parental health. BMI is not doing anything here. Smoking status is predicting that, and as well as HbA1c. Now getting down into these things, B0 is missing. So here, we wanted to get B0 to be positive, because then you can feel that the latent spatial factors do influencing the informativeness of the data. So you get B0 lying between this interval, 0.26 to 0.37, because these are the models that do consider the informative missing structure, where there is ES. Now look at B2 and B3. Remember, B1 was fixed at 1 for identifiability. So you get